So in this video we're going to look at nature of roots, and I think probably the biggest reason people struggle with this is that they're not really sure what the different types of numbers are. Right, so all the real numbers, and they're represented with an R with a kind of line down the side. We normally write it like this. Right, those are basically all the numbers that we encounter at school. For example, a non-real number occurs when you square root a negative number. So for example, the square root of -3, that's a non-real number. Right, and in many respects these fall outside of core maths. They do fall into AP maths, but they're outside of core maths. The other time your calculator will give you an error is if you divide a number by 0. I like to remember undefined if the 0 is underneath. All right, so those are numbers that fall outside of the real numbers. Now let's talk about two types of real numbers. All right, and they both are real numbers. Now rational numbers either end or they repeat, and they can always be written as a ratio of two whole numbers. That's where their name comes from. So for example, a number like 2,5, we can write that as 25/10. It's a ratio of two whole numbers. Notice it either ends or it repeats. A number like 7, we can write that as a ratio of two whole numbers, 7/1, all right, or 14/2. Right, a number like 0,333, carrying on forever. This one doesn't end, but it does repeat. This one we can write as 1/3. It's also a rational number. Okay, a number you might think like, well, what about 0,0007? Okay, well, that can be written as a ratio of two whole numbers because we just move it enough decimal places. It's actually going to be 7/10,000. Okay. They either end or they repeat. Irrational numbers never end and never repeat. And the kind of most common examples that we encounter at school are the pi, and then things like the square root of 2. But in fact, the square root of 3, the square root of 5, the square root of 13, the cube root of 5. All right. Something like the cube root of 8 is actually rational because the cube root of 8 is actually 2, and we could write 2 as 2/1. Right, these numbers never end, they never repeat, and you cannot write them as a ratio of two whole numbers. They, interestingly, are just as common as the rational numbers. The symbol for them is a Q with a little dash on. The symbol for the rational number is just a Q. Okay, now let's dive into nature of roots, understanding our numbers. All right, in the quadratic formula, this piece, and it's not given separately, this piece is sufficiently important that we actually give it a name. We call it the discriminant, all right, and we symbolize it with a triangle. You don't necessarily need to know that term discriminant, but it probably is worth knowing. I'll just quickly write it down. Discriminant. All right, and what it means to discriminate, as we know, is to kind of draw differences between, all right? So what the discriminant does, sorry, I wanted to write discriminant, not discriminate, but they come from the same root word, right? What the discriminant does is it actually allows us to discriminate between the different types of roots that we would get. If delta is negative, right, all of this makes perfect sense, as is the case with all maths. You can't find the square root of a negative number, and we have non-real roots. If delta is 0, our roots will actually both be -b/2a, right? Because we're either going to subtract or add the square root of 0, which is 0. Now, those are, we can see they're rational because they're written as a ratio of two whole numbers. Right. If delta is bigger than 0, then our roots will be unequal because we will be adding or subtracting a different amount. All right. However, if delta is bigger than 0 and a perfect square, for example, 25 square roots nicely, and our numbers, our roots, would be written as a ratio of two whole numbers. They would be rational roots. However, suppose delta was something like 13, all right? 13 does not square root nicely. It never ends and it never repeats, and our roots will not be written as a ratio of two whole numbers. They will never end, they will never repeat, and they will be irrational. If you understand this little diagram, then there's nothing to learn. If you don't understand it, try and learn it anyway, but it's much better to understand it. Now let's dive into solving some questions, and I've kind of scaffolded them. This is as easy as it gets. Without solving, discuss the roots of this thing. So the crucial thing, remember, and I'm going to write down the formula for delta is b squared minus 4ac. All right, that's our formula for delta. But remember that the thing needs to be in standard form. A is the coefficient of the x squareds, b with its sign, b is the coefficient of the x's with its sign, and c is the constant term with its sign. So this one over here, discuss the roots of this thing. The very first thing we've got to do is write it into that standard form, and we get x squared plus 2x minus 5 equals 0. Now we're going to work out delta, all right? And delta is going to be b squared, so it's going to be 2 squared minus 4 lots of 1 lot of minus 5. Right, and what we in fact get is 4 plus 20. So we actually get 24. Now we need to make a call on these roots. All right, it is bigger than 0, so the roots will be unequal. And it's not a perfect square, so they will be irrational. Right, I'm just going to go back up to that diagram just to show you kind of where we're at. Okay. We've got something like here. Non-perfect square, but bigger than 0. Unequal, irrational roots. Okay. Now this time, we've been told something about the roots. We've been told that this equation is going to have equal roots, and what will P be? Well, good practice, write down, if the roots are equal, we know that delta must be 0. All right. Now, in this particular case, delta is p squared, that's our coefficient of x, our b value, minus 4 lots of our a value is 1, and our c value is 16. And so we actually get p squared minus 64 equals 0. Right? And just be careful if you add 64 to both sides and then square root, that you remember to have the plus or the minus. In fact, this actually factorizes p plus 8, p minus 8. And we will have equal roots in this equation if p is negative 8 or 8. Right. They will also obviously be rational. Okay. So they'll be equal and rational. Notice that we don't need to say, if we talk about roots being rational, all right, so let's just go back up to here. If we talk about these roots being irrational, we don't have to say that they are real, all right? That's already implied. All irrational numbers are real. That's a little bit like saying something is a zebra and then also saying it's a mammal. We don't need to say that. Once we've said it's a zebra, we understand it's a mammal. It's not wrong to say it, but we don't need to say it. And in many respects, it sort of might indicate that you're not entirely sure the difference between irrational and real. All right, just remember the picture here. All rational numbers and irrational numbers are real. Right, this one says, for what values of m will we have real unequal roots? Well, let's put it into standard form first. X squared plus mx plus m plus 3 equals 0. All right, and we will have real unequal roots when delta is greater than 0. So let's have a look at what delta is in this case. Delta is going to be our coefficient of x, which is b, so our m, in other words, m squared minus 4 lots of a is 1. This is all c. It's all a constant. It doesn't have any x's in it. And we want this to be bigger than 0. Now this is in fact a quadratic inequality. Right? Remember how we solve one of these? Everything's connected to everything else in maths. We solve one of these, in fact, by factorizing it. Visualizing it, it's actually a parabola with a happy parabola, the right way up, what we call a concave up parabola, but we'll get to that in A block, right, with roots of -2 and 6, right? So in fact, the thing is positive above the axis when m is less than -2 or when m is greater than 6. That is when, this is an expression, just to make sure we understand what we're doing here, this is an expression of delta for different values of m. All right, delta on the sort of y-axis, and we want to be where delta is above the y-axis. All right, delta can't actually equal 0, because remember that if delta equals 0, then we would get equal roots. Delta must be strictly greater than 0. Right, let's take a look at this one. Show that the roots are rational for all values of k. So what we want to do, remember, we want to show that delta is a perfect square, irrespective of what k is. So let's have a look. Let's put it in standard form first. This is plus k minus 1. This is all our c values. So let's work out delta. We get delta is k plus 2, the coefficient of x, all squared, minus 4 lots of a, lots of c. And remember, our c is k minus 1. What this actually comes to, if we square it out nicely, k squared plus 4k plus 4 minus 12k plus 12. Right, now this simplifies to k squared minus 8k plus 16. We want to try and show that this is a perfect square. Let's see if we can factorize it. It clearly factorizes to k and k. Both signs the same and both negative. And we want factors of 16 that add to 8, and in fact they are both the same. So this is actually k minus 4 all squared. So we will in fact get a perfect square for delta, all right, for all values of k. So therefore the roots are rational. All right, if you want to, we've shown it's a perfect square, but we could say since delta is a perfect square. This one says, show that the roots are real and unequal. So what we want to actually, we must show that delta is in fact bigger than 0. So let's work out delta. First thing, remember, put it into standard form. X squared plus px plus p minus 2 is equal to 0. So in fact, delta is going to be p squared minus 4 lots of p minus 2. And in fact, delta is actually p squared minus 4p plus 8. Now, here's the thing, right? It's very difficult, in fact, it's impossible, to tell at a glance whether this is always positive or always negative. But remember, completing the square is such a powerful tool to help us get a sense of a number. Right, so what we're now going to do, and if you haven't watched the completing the square video, strongly recommend that you do. We're going to write this as something squared. It's going to in fact be p take away 2. When you square this out, you will actually get p squared, you'll get minus 4p, you'll get plus 4, which we didn't have before, so I'm going to minus 4, and then we've got our plus 8. Remember that plus 8 is just been copied down. This line is equal to the line above it, which is why there's an equal sign. This can actually be written as p minus 2 all squared plus 4. But this, all right, remember that when you square something, it can't be less than 0. In fact, it's got to be greater than or equal to 0. And then we're adding 4. So in fact, we've shown that delta is at least 4. Right? It can't be less than 4. It can be 4 if p is 2, but it can never be less than 4. Right? And because delta is bigger than or equal to 4, right, for all values of p, therefore the equation will have real and unequal roots. So in this question, the first thing we need to understand is that if we've got y equals ax squared plus bx plus c, which is kind of what all these parabolas are, in order to get a 0 over here, to have a standard kind of quadratic equation, what we're actually doing is we're making y equal to 0. And when we make y equal to 0, we are actually finding x-intercepts of our graph. Right, so these are all the x-intercepts. Right, now, if we start off and we look at this graph number 4, it doesn't have any x-intercepts. So there will be no real roots when we try and solve that equation. That would be delta 2 equal to minus 3. What we're doing here is we're matching different delta values to different graphs. If we look at graph number 3, it actually only has one root or two equal roots. And remember, our roots are equal when delta is 0. So graph 3 matches to delta 4 equals 0. Graph 1 and graph 2 both have real unequal roots. The difference is, though, that graph 1 has roots of -2 and 3. Those are rational numbers. In order to get rational roots, delta must have come out to be a perfect square. So delta 3 is 25. Graph 2, the roots are clearly irrational, and so delta must have come out to a non-perfect square. So this will be delta 1, which is 23. In this question, we've basically got a parabola looking something like that. I'm just going to draw it 3 times, and you'll see why now. And then we've got a straight line, right? And when we've got a parabola and a straight line, if we solve them simultaneously, then there's essentially 3 things that could happen. They could miss one another. The straight line could just touch at a single point, the parabola, or in fact the straight line could cut the parabola at 2 different points. And when we solve the equations simultaneously, we'll get a quadratic equation. In this case over here, the quadratic equation will have no roots, and so delta must be negative. In this case over here, the quadratic equation will have equal roots, so delta must be 0. And in this case over here, delta must be greater than 0. Now this question says, for what values of p will these two functions touch one another? All right, so in order to touch, we know that delta must be 0 for this particular simultaneous equation when we solve them. So what we're going to do is we're going to put them equal to one another. X squared plus x plus 3 equals px plus 2. We're solving them simultaneously. We need to get this into standard form first up. So this is going to be x squared plus x minus px plus 1 equals 0. Now, for the first time, we now need to just make sure that we know what our coefficient of x is. So what we're going to do, we're actually going to take out an x, right, because it's in 2 different places, and we get 1 minus p plus 1 equals 0. You may be more comfortable with me writing this like this. X squared plus 1 minus p lots of x plus 1 equals 0. This is in standard form, and I can now work out my delta. So let's do exactly that. Delta equals my b squared, my coefficient of x all squared, minus 4 lots of my a value times my c value. And what I get here is I get p squared minus 2p plus 1 minus 4. Right, and so in fact delta is actually p squared minus 2p minus 3. All right, and remember, I want delta to equal 0. So I'm now solving this quadratic equation. It factorizes very easily to p minus 3, p plus 1 equals 0. So p equals 3 or minus 1. Let's just take a look at what we've got here. This is a little simulation. There's the parabola, and here is a straight line, px plus 2, and I'm able to go and change the gradient. Notice at the moment, the graphs are not touching at all, but if I increase my p-value up to 3, you might remember we got 3 and minus 1. At 3, the graphs just touch. If I go bigger than 3, the graphs start to cut one another. If I go down to minus 1, which is the other value we got, you'll see that they again touch. All right, and then they would start to cut. So minus 1 and 3 are the 2 values at which the graphs touch, and those are the values that we've just found. So in this, our last question, we asked to sketch this function. Hopefully we're all comfortable that it is a parabola. The fact that a is bigger than 0 suggests that it's kind of a happy parabola, or what we call a concave up parabola in grade 12. Now, b on its own doesn't tell us anything, but remember that x equals minus b over 2a is the axis of symmetry of the parabola. Now, if a is positive and b is also positive, then this quantity is actually going to be negative because of this negative sign here. So in other words, we know that this concave up happy parabola actually turns on this side of the y-axis, on the left of the y-axis. B squared less than 4ac, well, that looks certainly a little bit like something to do with delta, and it absolutely does. That's why that's in this nature of roots video. If b squared is less than 4ac, then if we just subtract 4ac from both sides, what we're saying is that b squared minus 4ac is less than 0. In other words, delta is less than 0. Okay, and if delta is less than 0, that means that there will be no x-intercepts. So this is a concave up happy parabola, turns over there, doesn't have any x-intercepts. All right, and that brings us to the end of this little video. Hope you found it useful.